So today we will have three presentations. The first will be a PowerPoint presentation about how our equipment can be used for field studies, in situ use, and so on. And then I'll do a demonstration of the field microprofiling systems for how to do microprofiles in sediment. And then I'll do a demonstration of the software and how to use that to convert microprofiles into activities within the sediment. So today they will be about the in situ systems, and all our in situ systems, they have one thing in common, that is they use the in situ uniamp amplifiers for mounting the sensors and for establishing the pressure compensation. And I will get into detail with this first. Then I'll get into detail with the mini profiler and how to measure microprofiles in situ. Then go to the flux chamber lander and show how that can be used to measure sediment water fluxes. The third way we have to measure sediment water fluxes is the AD covariance technique. I will get into that as well. Talk a little bit about deep sea landers. Then about measurements in the water column. If you want to just profile the water column, you can also use our sensors. Then at the end, I will spend some time on working with very low oxygen concentration using the stock sensor, which can go very low in detection of oxygen. Yeah, let me start here. So as you saw yesterday, we have the field microprofiling systems which can take the sensors into field. So that's the first step. But we also have other systems that can take it all the way to the seafloor and to the deep sea as well. These are the pictures of the mini profiler, which can do profiles in situ. This is the eddy covariance system for sediment water fluxes or fluxes on the underside of the sea ice, as shown here, where it's upside down. And then there's the flux chamber lander. And then all of these systems can be mounted on these free-falling in situ deep sea landers. As I said, then yeah, we need the in situ amplifiers to take the sensors into the sea. You can, with the lab and the field multimeter sensors, you can go underwater. They are waterproof down to 10 meters, so you can actually do measurements if you send a diver down with them. If you want to go deeper, then you need the in situ amplifiers as shown here. There's the deep version and there's the shallow version for 300 meters. This one is all the way down to 6 kilometers depth. In situ amplifier has the electronics here. It has this connector up here for mounting on the instrument, and then it has the in situ connector here and the sensor here. In situ connector is necessary to establish the pressure compensation and connect the sensor to the amplifier. Pressure compensation is needed if you want to go deeper than 50 meters. If you want to take microsensors into the sea, you might want to measure microprofiles. You will need small sensors with small tip diameter to get a high spatial resolution. Shown here for a micro sensor on an in situ connector on the in situ amplifier mounted in the mini profiler. I also just want to measure bulk water concentration, so maybe profiling the water column. You can use standards unison sensors for that. Typically, we mount a stainless steel protection cap on these. This one is glued on and the tip is protected in here. And this one is a reusable protection cap, which sits with a compression fitting. You can take it on and off as you want. So the pressure compensation in the sensors is made in this way. So the sensors are built with an extra silver wire here that is connected. That one end is in the electrolyte, the other end out in the air, and then it sits in the glue here where the sensor is assembled. You can see it here in detail. So the outer blue is the casing of the sensor, the inner blue is the cathode, the green is the glue, and then the red is the pressure compensation wire that goes from the electrolyte and out. The idea with this one is not establishing a connection, is simply just to remove it so it leaves a channel in the glue, so there's connection in and out. This must be done before you mount it in the in situ connectors. This is the shallow one, and this is the deep one, and the one below is the shallow one. This is the shallow one with the sensor mounted, and the sensor is held in place by a compression fitting here. You can see these are the O-rings in the drawing that squeezes onto the glass. The blue is the outer glass. The blue here is the inner cathode. This in situ connector has an silicone rubber sleeve here and a hole on the side. and the interior and the silicone sleeve must be filled with paraffin oil. That is the brown down in the drawing here. And when this channel has been opened by removing the pressure compensation wire, then pressure increase around the sensor will be transmitted through the silicone rubber through the hole in the side here and into the oil, and the oil will then transmit the pressure through this channel into the inside of the sensor. And then the pressure will be exactly the same inside the sensor and outside the sensor. And then you can take it all the way to the bottom of the, to at least 6 kilometers depth, I think also even deeper. So all our in situ instrumentations are also operated via our software, the sensor trace suite that consists of these profile part is needed for the mini profiler, whereas all the other instruments are operated via the logger and the programming tool, which are freeware. The programming tool is a very simple to use and it's yet powerful programming environment where you have basically a toolbox out here. The tools available depend on the instrument you have. You can then pull the tools onto this sensor area here, connect them with arrows, and then they are executed in a sequence. That could, for example, be one here. I don't know if you can see it. It says steerer start. So this is for a mini chamber lander. This will make the steerer in the lid start rotating, and you can set the speed there as well. And another one will close the lid and so on, start the data logger. You can do loops and all sorts of stuff in this. It's really easy to use and powerful. And as mentioned, the profiling is what you need for the mini profiler, which I will. So just as when you measure microprofiles in the lab, you are interested in probably knowing oxygen penetration into the sediment. Where is the sulfide front? What is the pH in the sediment? And is there an electric potential indicator of cable bacteria and so on? So all our sensors can be used on the mini profiler. So this will allow you to calculate fluxes in the exact spot where the microsensor is introduced into the sediment. And you can calculate the specific activity in the sediment, so the activity is per volume of sediment, for example, nanomoles per cubic centimeters per second. You will get the activity for the sediment itself right where you measure, and almost not influenced by the macrofauna. So the direct effect of the macrofauna is not included here. And you can use it for diurnal cycles measurements because it's non-destructive and you can repeat measurements many times. So I will show examples of that, how that can actually be done. It comes in 3 different versions. So the basic version is the one-dimensional version, which you see here. It has the field data logger, which is the brain of all most of our in situ instruments. It's the sensor holder here for room for up to 8 sensors. We make them generally in a 4 or a 8 channel version. It has these 3 feet, so it can stand safely on the sediment. There is a motor located in here. I think you can see it here, which can move the sensor holder and the whole central unit up and down in steps down to 50 micrometers. So you can do fine profiling with this instrument. It comes in a 300 or 6,000 meters version. Dimensional version of this mini profiler has the same central unit here that can move the sensors up and down vertically, but it also has a second motor that you can see here, and it can rotate the spindle that will make the central unit travel sideways. So you can measure a series of profiles. You can measure a set of profiles, pull the sensors out, move it sideways, and then set the sensor, push the sensors in again and get a second set of profiles, take them out, move sideways, and so on. You can keep doing that. That's really powerful. And we also have a 3-dimensional version, which has a total of 3 motors. So one motor that will move the sensors in and out, one motor that can move the whole central unit here sideways on these 2 poles, and a third motor here that can move the whole thing back and forth on this pole and one hiding behind. You can measure profiles in a grid, and then you can really get many profiles in one deployment. This one is mounted with an ROV handle. We can do that for all the different systems so an ROV can grab the profiler and place it on the seafloor. And then there is an ROV switch as well, which is has this arm. So the ROV operator just needs to hit this somehow, and then as soon as it's hit, then it triggers the field data logger, and it will start the program that you have made before the deployment. It will run the program, and you can pick it up again afterwards. Come with some data examples. Here the mini profiler has been used on an intertidal flat in the English Channel in France. For 6 days, they were continuously profiling, getting 900 oxygen microprofiles. Are some examples of the microprofiles here. This is microprofile in dark, and this is one close to noon, so in daylight. And this intertidal flat was inhabited by microphytobenthus, so it was photosynthetic, so therefore they peak in oxygen in daylight. They followed this, as I said, over these 6 days. You see up here this waveform, that is the tide, so the water depth. The horizontal line here is the sediment surface. So when the water was higher than the sediment surface, it was flooded. These are the gray bars here. Down here you can see the light intensity also. So there's darkness here and sunshine here and so on. It goes up and down. And from the profiles, they calculate the net oxygen production. Notice, you should know that the 0 line is here. So here's a positive production, here's a negative production that coincides with darkness. It's a nice way of investigating such a system without affecting it, and you can get a lot of measurement in a short time. Another example of a mini profiler that is from the southern Atlantic of Congo. This station was at close to 4 kilometers water depth. You can see there are lots of profiles being measured here. They are relatively similar. Oxygen penetrates to 30 to 40 millimeters, so relatively long. On this lander, they also had a flux chamber, not a Unisense one, a home-built one, but we also produce these if you're interested. And then they calculated the oxygen consumption rate. The black ones, that is the diffusive oxygen uptake, so calculated from the microprofile, so in the exact spot where the profile was measured. And the white ones is the total oxygen uptake calculated from the flux chamber. So that includes macroorganisms, also the fauna. And the difference between the diffusive oxygen uptake and the total uptake is often taken as an indication of the activity of fauna. So, and the ratio between these two is often calculated and taken as an indication of the activity of the fauna. One third example of data from the mini profiler is from an intertidal flat in the Arcachon Bay in France off Bordeaux. In this area, when the water level is low, at low tide, then there are these pools left behind because there's deeper sediment here. You can see on this aerial photo that all the darker areas, they are the pools that are left at low tide. So this is one of them. They placed a mini profiler there for a couple of days and measured. Start down here, this is the water depth. So you see there's high tide and low tide and high tide. And the period with low tide, that is when the tidal pool is isolated, so it becomes a pool. In the other parts, it's in connection with the water flowing around. The next here shows the light intensity. So in the yellow areas, there's light. In the white areas, there is darkness. So starting from above, this is temperature. You see when everything is flooded, then you have the same temperature all over. But when the pond or the pool gets isolated from the rest, then it warms up. The same happens to the oxygen. You can see here, oxygen concentration increases both in the water and in the sediment, and the oxygen penetrates even deeper. See the black line here is the oxygen penetration, so it goes deeper into the sediment. When it's flooded, then it gets back to homogeneous. Also measured sulfide, you can see here, and the black line indicates the front of the sulfide zone. And the interesting thing here is that there's about 10 to 15 millimeter distance between the bottom of the oxic zone and the top of the sulfide zone. So there's a sulfide-free area in the sediment. And they speculate in the paper that it's probably because of the activity of cable bacteria that removes the sulfide in this 1 to 1.5 centimeter zone of the sediment. They didn't have the electric potential measurement here. That would have been great. That could have shown this more clear. So another way of working with the sediments, that is to use chambers to get sediment water fluxes. You can use sensors. You can use all the unisense sensors. You can also use the under-row sensors, which we integrate with our system for oxygen conductivity, depth, and turbidity. There's also a water sample typically on these systems. You can take water samples during the incubation, 12 of them normally, and they're 16 milliliter each. You get a flux estimate of a larger sediment area, and that will include whatever flora and fauna that has been enclosed in the chamber. And again, you can use the ratio of the flux calculated from chamber measurements to that calculated from the microprofiles as an indicator of the faunal activity. A mini chamber lander normally looks like this. It has the chamber, polycarbonate. It has a lid with sensors. It has 2 magnets here that will allow you to deploy the system with the lid open so that it can settle, and disturbances caused by the settling can go away before you close the lid and start the incubation. It has adjustable feet that will allow you to adjust the penetration of the chamber into the sediment. It has a water sampler. It has the field data logger, which is the brain of everything. It controls it all, and a holder for an extra battery pack. Closer look at the lid, you can see that there are this is open because the magnets are together here. You can polarize the magnet here and then it will close the lid. And that's really smart, because when you deploy, you will always disturb the sediments a little bit, and you can get fresh water flowing around it for maybe half an hour before you start the incubation. There's a rubber seal here that makes sure that the lid seals very well to the chamber. Also, I should have shown that there's a motor here that can rotate the steerer that sits under the lid. You can see it more clear here, this cross made of POM. You can vary the rotation speed as you want, and direction as well. Here are a number of under-row sensors placed in the sensor in the lid. This is a conductivity and oxygen and a turbidity sensor, I think. And there are a number of holes where you can place unisense sensors. And the dark shadows here in the white lid, those are magnets, and on the rim here there are also magnets. So when you close the lid, these magnets, they really close the lid very well, so it's watertight. There's a water sampler on these as well, 12 syringes looking like this. It can be used either for sampling or injection. You could, if you want, make experiments during an incubation. You could add nitrate or dissolved organic matter or whatever you want and see the effect of that. You can also use the injection syringe for a determination of the precise volume of the chamber. Typically, you will take the second to last, so the syringe number 11, inject a tracer into the chamber, let the chamber steerer rotate for 10 minutes, and take syringe number 12 as a sample. And from the concentration in that one, you can then calculate the dilution of your tracer, and you can calculate the accurate volume of the chamber. These are some data examples. This is from a study in the Bay of Gdansk in the Baltic Sea. They worked on 6 different stations here. They had an oxygen sensor. You see the data from that here, and they also took water samples, as I will show. As you can see, during the incubation, the oxygen concentration decreased in all of them. For example, the red one here, station VE04, and that is the one over here. So this is calculated oxygen consumption rate from the decrease in oxygen. Last line here, that is VE07, which is the one with a very low oxygen consumption rate here. This is a very easy deployment, very safe deployment to do. You'll always get good data from these oxygen decrease data. These are data from the 12 syringes. So they were sampled during this incubation. This is from stations VE02 and VE04. They analyzed the water samples for nitrate, ammonia, silicate, and phosphate. And you can see, for example, the silicate would increase in both stations. So with the ammonia concentration, whereas nitrate, the red one, would increase a bit here, decrease a bit here, and so on. You can do all the analysis you want. You can, for example, analyze for dissolved organic matter, DOM, DOC, or you can analyze for trace metals or whatever you want. So any kind of chemical analysis you can do, you can also do here. So we have a third method, as I mentioned, for working with sediment water fluxes, and that is the eddy covariance method. This is a really non-invasive method because it actually doesn't touch at all what it is measuring. It measures the result of processes occurring upstream from where the sensors are placed. Typically, they are used for oxygen fluxes, either with an electrochemical or optical oxygen sensors. You can also use them with other fast responding sensors. It could be sulfide, it could be hydrogen, but I don't think there's anywhere hydrogen is relevant. It could be temperature also if you want to measure temperature fluxes. We'll estimate the flux from a very large area of sediment, typically between 5 and 100 square meters. I'll get back to how that is calculated. And when you use this, you include the whole community, including the sediment, the large flora and fauna, etc. You can use it in seagrass beds, mussel beds, and so on. And I will show examples of that. So basically, it consists of this tripod with the instrumentation and the sensors on. This has the Nortec vector here, which is an acoustic 3D current meter. You can see it down here. It will measure the flow rate and direction, so 3D flow rates of water in a very small volume of water right in front of where the sensors are placed. In this case, we had 2 Clark type sensors and 1 optical oxygen sensor on the instrument. And then there's of course the field data logger, which again is the brain of it all. And then there was a field uptode meter operating the uptode here. Yeah, and that was it here is placed out in a river, so it's measuring the fluxes here. I'll shortly describe the principle here, and I'm not what do you call it, an oceanographer. I don't have the tools to do all these calculations, but I'll show you the principle of these, and you can get to the papers if you want to know the details behind it. So this acoustic current meter will measure the flow direction and speed here in this volume. The microsensor will measure the oxygen concentration right next to the volume. This must be done very fast. We operate at 64 Hertz, so 64 times per second we do this measurement. And the principle of the flux calculation is that for each of these small time steps, if you multiply the vertical flow rate with the concentration of oxygen, then you'll get the transport of oxygen in this short period of time past the sensor here. If you summarize this over a longer period of time, you will get real flux rates. But it's not exactly how this is done. I'll just this was just to simplify it. In this slide from the Peter Berg paper here, you can see the so-called Reynolds decomposition is used. That means that a concentration can at any time be expressed as the average of a concentration plus the deviation from this average. And the vertical flow rate can be expressed as the average of the vertical flow rate and plus a deviation from the vertical flow rate. And then the eddy flux is simply calculated as the product of these two, the deviation from the average concentration and the deviation from the flow rate. Now, this shows an example where there's a sediment with benthic microalgae. There's sunshine, so there's an oxygen production. That means there's oxygen released from the sediment. There's water current going in this direction, creating some turbulence. The sensors are sitting over here and measures whatever has happened up here. What they do is, so in the yellow colored ones here, this is the vertical velocity, and this is the oxygen concentration. When the vertical velocity is negative, then the flow rate is toward the sediment. If it's positive, it's away from the sediment. And you can see here the yellow ones, that's towards the sediment. That coincides with oxygen concentrations being lower than the average. When the water comes from the sediment and up to the water column, in the blue parts here, you see there's higher oxygen concentration than this is because there's an oxygen production. And this can be used to calculate then the accumulative oxygen transport as accumulated here over time. This is only 60 seconds, but normally you will do it in longer periods of time. Show this here because this shows the opposite actually. So this is a heterotrophic sediment. Here the oxygen concentration is highest when the flow rate or flow direction is towards the sediment. When the flow is from the sediment and up, then oxygen concentration is lower because oxygen has been consumed when the water was in touch with the sediment. This shows the data. It's difficult. You cannot see all data here. Actually, this is 1 hour of data, and that is 230,000 data points. So therefore, it looks a bit messy. Blue line here indicates the vertical flow velocity, and the red and the green the horizontal flow velocities. This indicates the oxygen concentration, and this indicates the cumulative oxygen flux over time. So the flux has been calculated for every time step in these and divided into quarter of an hour periods. This is then recalculated into per unit area. And those four are averaged into represent the full hour from 14 to 15 here, and you have a standard deviation on this as well. So this is a nice demonstration of how it can be used to calculate fluxes. The big advantage of this technique is that you can work with very heterogeneous environments. Here it has been used over a coral reef, and you can see this is very heterogeneous. It would be very difficult to get a flux chamber or anything similar into this, but the eddy covariance can measure the fluxes. Station A and B here, and the data are shown over here. This line with the open symbols, that indicates light intensity. So during daylight, there's a release of oxygen from the coral reef community. And during nighttime, there's an oxygen uptake. The pattern is the same at station B, but the activities are a bit lower, and so is the light intensity. This one was a little bit deeper than this one, and there's also less dense community. So this is a way of getting data that would be really, really difficult, if not possible, to get in other ways. The system may also be used in a totally different environment. This is a deployment of eddy on the at 80 meters water depth off the coast of the States, Oregon it is, yeah. Here you see it's a bit different data set, but this is the water depth. So there's a tide of about 2 meters amplitude. These are the horizontal flow rates. You can see the horizontal flow changes quite a lot during the incubation. These are oxygen and temperature shown here, and these bars are the calculated oxygen uptake rates. They vary quite a lot, but in this paper, there's a lot of details in this paper, but they get a very good agreement between the oxygen flux calculated from the eddy data and the wave height on the sediment, on the water surface 80 meters above the sediment. And this is more or less what you can see here. Also, you can see the horizontal flow rate suddenly starts to change because there's wave action being propelled all the way down to the bottom. So it's a very versatile tool also for deeper sea work. As I mentioned, the footprint from this that you measure from a relatively large area of sediment, this can be calculated, typically 5 to 100 square meters, but you can calculate the actual footprint. Peter Berg has described this, but I will not get into detail. I just mentioned that the sensor height above the surface affects this the size of the footprint very much. You can see the calculated footprints here with the sensors 5, 10, 15, 20, 25, and 30 centimeters above the sediment. So the higher above the sediment the sensors are, the larger is the footprint. So you can also utilize that to determine where you want to get your data from. Then it depends a lot on the flow conditions and on the sediment roughness as well. But again, go to the paper and see the calculations. We have, as I mentioned, there's a lot of data in this, but we also have a software that can handle these data. This is based on the Peter Berg calculations actually, and I will not get into detail with how it works. There's a manual that can explain that to you. But there are a number of parameters you can set here. A few of them I would like to mention. So you can rotate the data set mathematically, so the flow will be directly from the front of the sensor. that is normally done. You can do a compensation for changes in oxygen concentration during the incubation. So normally we would assume that the flux of oxygen through the layer where the sensor sits will equal the flux through the sediment water interface. But this is only the case if the oxygen concentration or oxygen inventory has remained constant between the sensor and the sediment. If it has not, then you can do a compensation for that. You can do a time lag compensation that will correct for the fact that the sensor is sitting not at the exact point where the flow rate is measured, and that can be corrected for as well. This is the frequency of measurements. Then you can make a running mean, because we will need to calculate deviation of oxygen data from a mean concentration, and you can set the running mean, the sort of the period you want for the running mean. In this case, it's 1900 data points, about 30 seconds. And you can split your data set into several intervals. In this case, I've chosen to split the data into a quarter of an hour intervals. So I think there were about 12 hours in this data set, so you'll get 48 periods of fluxes. What you get from this software is this. You get first the velocities. The blue is the vertical velocity, and then the other two are the horizontal velocity. You get the data as the red one shows the oxygen data as they are measured. The blue one shows the running mean using the period you have selected over here. And the green line shows linear regression through all the oxygen data. And down here, it shows the cumulative oxygen flux for two different types of calculations. Up here, there are three different types of calculations. As I mentioned, you need to multiply the deviation of the oxygen concentration from the mean. So you can do that in three different ways. One is to take the global average of oxygen concentration here and calculate the deviation from that. That's not a good idea normally if you have a change in concentration during the incubation. This is the one plotted here as flux number one. Flux number two is calculated using the linear regression as the average. So for each data point, the distance between the corresponding linear regression value and the measured value is calculated and summed up for the red line down here. So the increase in oxygen uptake over time. And then number three up here, that shows the flux calculated, where the deviation is calculated between the running mean and the actual data points. So there are, I think these different ways of calculations can be good in different environments, and you will need to make a scientific decision on which way to do this. And I forgot to mention the green one here is the cumulative oxygen flux measured from the run. Okay, so these three methods for working with sediments are complementary. The microprofiles, they give you information about vertical distribution of solutes, consumption, production rates in the sediment. You can use it with all our sensors. You can repeat measurements because of the very low sample disturbance. You can investigate interaction between solutes and organisms you find in the sediment. The microorganisms do not really affect the rates that you calculate, and it's very much in situ conditions when you do it this way. The flux chamber lander, well, that is more for a community metabolism measurement. So anything that has been captured within this 30 by 30 centimeter chamber, that will contribute to the fluxes you measure. Have a continuous recording with sensors, and you can calculate production and consumption of solutes from that. But you can also take water samples and analyze any solute you want. You can do injection for experiments, and this is also very much in situ conditions. This is the anticovariance is the most non-invasive of them all, because it really doesn't touch what it is measuring. It has natural light, there's no shading, so you can analyze annual or diurnal cycles very easily. You can work with very complex communities, also permeable sediments where there's a pore water flow through the sediments. That would, in most cases, be cancelled out if you use a flux chamber lander, but you will see it with the profiling system. Then you can work generally with oxygen sensors, also with temperature and sulfide sensors and other fast sensors, very much under in situ conditions. All these three systems can be deployed or mounted on a deep sea land. This is sort of a frame with a flotation unit, and in this case a mini profiler is mounted here in the center. This is a 3-legged version, this is a 4-legged version. It has a bucket with scrap iron actually in each corner, about 50 kilos each. This weight will give a negative buoyancy when you drop it from the ship, so it will sink to the seafloor. And then you can release this weight again, or ballast, and then it will get positive buoyancy and come back to the surface. You can release the buoyancy, oh sorry, the ballast, not the buoyancy, the ballast in different ways. You can release it programmed from the field data logger through a burn wire. You can use an acoustic release system if you want. Typically you want 2 of these, so you have a backup if one fails. You can actually see the acoustic release units sitting here between the flotation units. And you can also mount a magnesium bolt for safety. That will dissolve after a couple of days, and then it can release the ballast and it will float to the surface. In order to find this, if it's floating around in the middle of the Atlantic, you will need some kind of help. Typically people mount GPS transmitters, a radio beacon, and radar reflectors on it, and a flag also. When you get closer, you can see it. And people typically find these again when they have deployed, and it's very seldom they get lost. So, and the reason to use this and go through all the hassle of using such an in situ one, that could be, so I could argue for that with this study here by Ronnie Gluth et al. They've been the pioneers of a lot of this in situ sediment work. You can see oxygen profiles into the sediment here, measured in the lab of samples retrieved from the site and measured in situ with a lander. And there's quite a difference, 2 millimeters oxygen penetration in the lab and 6 at 3,000 meters depth of Shelton, Chile. Did this more systematically and took sampled a lot of different stations at different depths. And they found this ratio, so the oxygen penetration in the lab relative to the oxygen penetration in situ. In shallow waters, you get the same, but if you go deep at 5 kilometers, for example, there's a factor of 5 difference. So you get only 20% oxygen penetration in the lab compared to the in situ one. So this is very much in line with the examples over here. When you then calculate the diffusive oxygen uptake, you get an overestimation of the diffusive oxygen uptake in the lab relative to that in situ, up to a factor of 3.5 at 5 kilometers depth. So that's a good reason that if you want the actual oxygen penetration and respiration ratio, you may want to work in situ. So as I mentioned, we can also use our sensors just to measure water column profiles or anywhere in the water column you want to work. We have this field data logger mini, which is a simple data logger with either 2 or 4 channels. 4 in this case. The sensor is mounted via the in situ amplifier here and with a stainless steel protection cap for protection. It can be used with all Unisense sensors. It has support for the stock sensor as well, as I'll show in a moment. It comes in a 300 meters or 600 meters, 6,000 meters depth rating. It's battery for up to 20 days of operation, and you can also interface it with the CTD or other equipment if you want the signal together with the signal from a CTD, for example. You can see it on deck of a ship. It's a relatively small cylinder that's easy to get room for in CTD or rosette sample or wherever. This example, it has been used and deployed with an ROV around hydrothermal vents of Japan, I believe, at 2.4 to 3.3 kilometers water depth, measuring hydrogen sulfide and hydrogen around these vents. You can see these organisms thriving around the hydrothermal vents, many of them living from sulfide or hydrogen as energy source. Just show this table that data you can get from it, which are difficult to get in other ways. For example, here at this Kairai field, there was 20 to 44 micromolar of hydrogen, and there was 137 to 211 micromolar of sulfide. In this Edmonton field, it was a bit different, so almost no hydrogen below half a micromolar, but still up to 127 micromolar sulfide. So this is a way of taking the sensors into the sea and get measurements with these. Then I'll talk a little bit about the stock sensor, which is the switchable trace oxygen sensor that can get detection limits down to 5 to 10 nanomolar of oxygen. And this is really important, as I will show in some studies. Briefly mention how it works. So it's actually two sensors in one. The inner sensor, which is in red here, this is the outer glass, and the cathode here, that is the measuring sensor. It has a silicone rubber membrane in the front. This is placed inside another sensor, which we call the front guard, which has also silicone rubber membrane here and a large porous gold cathode here. When this gold cathode is switched on, it will catch all the oxygen entering the sensor, and no oxygen will get into to the measuring sensor. So that will give a zero signal. When this one is switched off, then oxygen will pass through the porous gold here and get measured here in the measuring sensor. So we'll get a measuring signal as well. You can see it in a micro photograph here. So there's the front silicone rubber membrane here, the guard cathode sitting here, removing oxygen if it's switched on. Then there's the inner sensor here with the silicone rubber membrane, and right behind that there's the gold cathode, which is the measuring cathode that gives this signal for oxygen. The way it's operated is that the front guard is switched on and off in a very rhythmically, as shown here. In this case, there's 40 seconds on, 40 seconds off, approximately. So when the front guard is on, as here, then the sensor signal, the blue one, is very low. When the front guard is off, then the signal rises, and you get a reading for the oxygen concentration. Then front guard is on again, and you get a zero signal. Front guard is off, you get a reading again. In this case, in a little experiment where I added some 1.37 micromolar of oxygen, I did that twice, and that gives an increase in signal, as you can see. So the signal we work with here, the oxygen signal, that is actually the difference between the sensor signal with the front guard off and the front guard on. So that is, we subtract the zero signal already from the start, and we call that the delta oxygen signal. And that, of course, increased when I added oxygen here. I'll show this in a bit more detail. So this here indicates a period with the front guard off, front guard on, front guard off, front guard on again. So when the front guard is off, the sensor receives oxygen and measures this. The front guard on, you get the zero signal, and so on. This is in the presence of oxygen. In the absence of oxygen, you see, then there's no difference in the oxygen signal between the period with the front guard off and the front guard on. That means that the delta signal will now become zero. And this is an important thing for the way the sensor works, because when you calibrate the sensor, you know that the sensor will always give 0 millivolts for 0 oxygen, so that you already have one calibration point, so to say. You know that will go through the origin here, 0.0. So you actually, and since the sensor is linear, then your oxygen concentration is proportional to the delta signal, and you can do it with a 1-point calibration. And this is very handy now and then. And you can actually calculate concentration by dividing the delta signal with the slope of the calibration curve. So very simple. I'll show an example of how this has been used in a study I participated in a long time ago in the Pacific off Chile and Peru. Here there's a so-called oxygen minimum zones that's shown over here in this in red here. So there's a large volume of water here that's very low in oxygen. It starts from about 100 meters depth and is then 200 to 300 meters thick, and it's a very long part of the zone along the coast here that is low oxygen. On this cruise, we sailed along the coast most of the time here, and we did some measurements with the stock sensor and a lot of measurements with the seabird oxygen sensor. This was in the very beginning of the stock sensors. This was one of the first stock sensors ever used that was deployed here, together with a precursor of the current field data logger mini. We measured here stations up to 130 kilometers off the coast, and then a station much further off the coast. Those closer to the coast, you can see there's a volume of water from about 100 meters depth down to 300 meters depth, where we cannot find any oxygen. So it's not different from the detection limit here. less than 5 to 9 nanomolar in this study. When we got further away from the coast, there was a little bit of oxygen in this oxygen minimum, typically between 25 and 15 nanomolar, but very consistently. Because we had the stock sensor, we could recalibrate the seabird sensor, so we could get a detection limit of around 90 nanomolar. And you can see this shows, this area in the center shows the part that has oxygen lower than 90 nanomolar, and this is on the whole transect all the way here. This part is about 1600 kilometers, and it's about 200 to 300 meters thick. We had, as I showed, oxygen stock sensors on some stations, and there we couldn't see any oxygen, so that was below 5 to 9, so that may also be the case in the rest of this oxygen. We wanted to know how these very low oxygen concentration affected the nitrogen cycling in this area. So we did experiments measuring denitrification and NMOX. We did that in these glass reactors where there is a piston made from PVC but covered with glass here, so that we could take samples through these tubes without introducing head spaces, so we could just lower the piston. This is important for the N2 measurements we need for the processes. Then we could manipulate and monitor the oxygen concentrations through the stock sensor here, and we could add oxygen if we wanted. Typically, it looked like this, so we would fill the reactor, and during that we would contaminate the water a bit with oxygen. In this case, about 40 nanomolar. To get rid of that, we bubbled with helium for a little while, and then we got very low in oxygen. Then we added the 15N tracer, and we could follow the production of 29 and 30N2. From isotope pairing calculations, we could calculate the NMOX and denitrification rates. I'll not show the calculations, but we did a lot of these experiments where we added oxygen, so we held it at different oxygen concentrations, relatively constant. And from that, we could calculate how much the different nitrogen processes were inhibited by oxygen. Up here we have the N2 production by denitrification. You see it gets, and this here shows the inhibition in percent. So it gets inhibited already 50% at around 200 nanomolar oxygen, and fully inhibited up here already at 1000 nanomolar oxygen. We could calculate from the curve fit that this C50 was 209 nanomolar, 205 nanomolar. The data for the N2O production by denitrification was not nearly as nice, but we still did the fit, and we also did it down here. In this case, the N2O production was inhibited 50% at around 300 nanomolar oxygen, and N2 production by NMOX was inhibited at about 50% at about 900 nanomolar of oxygen. We extended this experiment also to include the nitrate reduction to nitrite, which is also an anaerobic process that had the same 50% inhibition roughly of 740 nanomolar. And we also looked at the aerobic processes that require oxygen, so the ammonia oxidation to nitrite and nitrite oxidation to nitrate. And in both cases, we were below 1 micromolar, 330 and 780 nanomolar oxygen. So this means that in this area, at least, the whole regulation of the nitrogen cycle takes place at oxygen concentration below 1 micromolar. So this shows the importance of having a sensor that can actually measure these concentrations. Back then, as I mentioned, it was in the early days of the stock sensor. We had quite a lot of instrumentation and cables and stuff, but this has become a lot easier since then. The stocks sensors are now supported by the UniAmp series of instruments, so it's just plug and play. You have a stock sensor, plug in one connector, and that means that you can enable the stocks mode in the software, and you can set the 0 on and off time for the front guard here, and you can just run experiments. We have also made it easier to handle data now. There was quite a lot of work in Excel with long experiments. This is a typical data set from a stocks measurements. You see the blue line going up and down because the front guard on and off. The red is the sync signal that shows when the front guard is on and when it's off. That's needed to analyze the data. In this case, there was oxygen added here. We had a high oxygen removed here and low oxygen and increased again and so on. The way this works is that, then if you have a stocks data set, then you will have access to this analyzer here. It's not shown if you don't have a stocks data set. What you need to do is you need to define the periods in the data set where you want the 0 signal and where you want the measurement signal. This is done by pulling these sliders by the mouse. In this case, I've pulled them so that the end of the zero signal is the last data point before this zero is switched off. The front guard is switched off, and then the first is 5 data points in front of that. So this will, the average of these 5 will be the front guard on signal. The front guard off signal, then I've pulled the sliders over here. So the last data point before the front guard is switched on, and then 5 data points before. This is all accumulated down here, so you get the time of the measurement, you get the zero mean, and that will actually be the mean of the zero before and after a measurement. And then you get the measurement mean, so that is the average of these 5 points, and then it calculates the delta signal as well, and there's standard deviation on all of it, and you can export it to Excel. So it's very easy to work with. That was the last part of the presentation. If you have any questions, then I will be happy to answer, and you are welcome to open your microphone, switch on your camera, and ask questions, and you can also do it in the chat if you want, and then we will.
Hello, thanks for your talk. And I
Yeah.
am curious about knowing when the equipment that is landing in depth, how you can be sure that the sensors are really in the top of the surface of the sediment? Because yesterday you mentioned that you can use even a microscope.
Yeah.
So how can you be sure that in the deep?
Well, what you do is that first of all, you'll need to probably place the sensors up a little bit high before you do the deployment, so you are sure they are above the sediment when the lander is landed on the sediment. Then you can start the motor. They can easily be done from the programming tool. Then you'll start the motor and move the sensors downwards continuously. You will then monitor the signal of one sensor, for example. It could be an oxygen sensor that you place a little bit in front of the others, or it could be a conductivity sensor, which we also have. That's a macro sensor. And then you will continuously monitor the signal. As soon as this sensor touches the sediment, then the signal will change. And then you will have programmed the field data logger to stop the motor when this happens. And then you know, okay, now this sensor touches the sediment surface. And then probably go back a millimeter and then start your fine scale profiling. And if you're out in an area, you know, for example, some of these, we know maybe the oxygen will penetrate 4 centimeters in the deep sea. Then you would maybe set the profiling to be 5 to 7 centimeters. And then it will do fine scale profiling for that and pull the sensors up again. And then if you have the 2 or 3D profiler, then you can move the sensors sideways after taking them out of the sediment, and you can do another set of profiles. Then you know roughly the position of the sediment surface. So the idea is that you analyze the data with the motor running, so the sensors are moving continuously, and then as soon as they change in a way that you have told it to, that this indicates sediment surface, then it stops and starts the profiling sequence. Yeah. So you can place the sensors up high, so they are safe when you deploy, and then you can run them down towards the sediment. Yeah, so that's typically the way people do it.
Okay, thanks.
Yeah, good morning. I'm curious to know about your landers and the stability once they land on the seafloor. Mm-hmm. If you ever have any issues with them sinking in, because if you're measuring 50 micron steps and the lander sinks in 2 millimeters over 2 hours, then you might have an issue.
Yeah, the experience seems to be that the lander sinks in during the short period, so the first few minutes, and then it actually stays there. So you will typically leave, I don't know, 15 to 30 minutes between the time you expect it lands on the sediment until you start your profiling. Yeah, so that's, and also depending on the sediment softness, you may need to have a larger feet. So some people, if they're out in very soft sediments, they may mount a wooden boards on the feet so it has more support. But that depends a lot on the sediment. Typically, people do some box coring or multi-coring of the sediment before they do the deployment to see what type of sediment is this and how should we operate the lander. Yeah. Thank you very much for listening. See you soon.